to have a look at how to model some nonlinear data, we're going to open up our fish data set, 6 fish. Let's change the name of this to something we'll remember, like fish. And load that data. We can take a look at the output data here. We have lengths and weights of fish. Lengths in inches, weights in ounces. And in order to understand this a little bit better, let's have a look at it on a scatter plot. Fish data, x is our length, y is our weight. We're trying to predict the weight of the fish using the length of the fish. Okay, so we'll run this, and there is a look at our data. So what have we got? Well, we've got a pretty, it's actually pretty close to linear, right? We've got close to a linear relationship between length and weight. You know, a straight line would fit this reasonably well, but it certainly wouldn't be perfect, right? We've got a definite curve to that data. So one way that we can fit a curve to this data is by using what we call polynomial modeling, where we add in successive higher order powers, higher order exponent powers of our x variable until we don't need any more. Okay, so let's see this in practice. We want to open linear models, linear regression here. Dependent variable is weight, continuous variable is length, and under model we'll add in just length for now and run this model. And what we're going to get is, well, not a bad model, right? It kind of looked like a straight line was going to be a decent fit, and indeed we've got a R-squared or adjusted R-squared of just under 95%. It's almost 95% of our variation in this data is being explained by the model. Alright, not bad, but we might be able to do better. And one of the ways in which we can see that we could do better is by looking at the residuals here. So our residuals, remember, are the leftovers after we have done regression. The residual is equal to the actual value of y minus our predicted value of y. If we scroll up first, here is that scatter plot of the data, and the line here is that regression line that we've estimated through this data. But notice that right around the middle of the data, we're consistently over-predicting our data. We've got a negative residual around the middle of our data because our actual is lower than our predicted. But at the ends, we've got the opposite thing happening. At the ends, we're under-predicting our data, and so we've got a positive residual. The value of the actual observation is greater than the one that we're predicting, given by the straight line. Okay, so let's then take a look at our residuals a little bit closer. We've got this U shape to the residuals. When you see this, this is a strong indication that you've got non-linearity in your data. And one way to model this is through polynomial modeling. Okay, so let's have a go at that. We're going to go back in here to our model effects and add in a squared term. So polynomial of order 2. Length and length squared are going to be our independent variables. Let's hit run and see what happens. Now remember, we had an adjusted R squared of about 95% previously. Now we've got an adjusted R squared of about 99%. So we have explained, let's see, there was 5% unexplained, now there's only 1% unexplained. We've reduced the amount of unexplained by 4/5. Okay, so our model's clearly better now. Is it good enough? Well, we can again look at those residuals and ask ourselves, is there anything, any pattern? It's not an obvious pattern anymore, though perhaps it looks like we've got all positive residuals up here and more negative residuals toward the middle, and then some positive residuals there, perhaps. Our procedure for doing polynomial modelling is not to stop once we've got a good model. Heck, we could have stopped with just length. That was a good model. But we keep on going until we can determine that adding any new variables, new polynomial variables, is not useful. Okay, so now we're going to add in length cubed and see if that has a good effect on our model. Does it improve our adjusted R-squared? Does it improve, well, here, this is saying it's improving our Schwartz-Bayes criterion, so that seems like a plus. We have our adjusted R-squared went up from just under 99% to now 99.16%, so we've explained about a sixth of what was left unexplained. And down here, this is our real test. Length cubed is significant in our model. So this is telling us that, hey, adding length cubed was a good thing. Our model improved when we added length cubed. Okay, well, can we keep going? Should we add length fourth, length fifth? Well, our procedure is now to keep adding one by one and see if each additional variable, each additional polynomial term improves our model or not. Well, right on this first page we see bad news. Our Schwartz-Bayes criterion got better as we added the extra variables, but it got worse as we added length fourth. Our adjusted R-squared was 99.16, it's still 99.16, so we haven't improved our model by adding the new variable. And length fourth is not significant in our model. So what we do now is we say, hey, that was too much. Adding length fourth was unnecessary. We should take that out. And then this is our final model with length, length squared, and length cubed. One last thing I want to point out here. If you happen to find that length and length squared, length and or length squared are not significant, have p-values bigger than 5%, ignore it. We need to have those lower order terms in when we have the higher order term. Otherwise, our model is estimated inaccurately. So make sure that you include the lower order terms whenever we include one of these higher order terms. So if we've got length cubed, we need to include length and length squared. If we have length fourth, we